Hello, good evening, good afternoon, and welcome. I'm very pleased to be joined by Paul Perera. Paul is co-founder and chief sustainability officer at Fluxart. So welcome, Paul.
Nice to meet you, Nadeem, and thanks for your time and looking forward to this conversation.
Thank you. Indeed, you're going to be speaking at the forthcoming Sustainable Aviation Futures Congress, or SAF Congress, which is fast approaching us, 7th to 9th of June in Amsterdam. So could you give me a little bit of background, maybe first to yourself and your own personal background, and then maybe let's get into the sort of interesting technology that Fluxart are developing.
So yes, thanks, Nadeem. I've been an aerospace engineer for the best part of 33 years, and I lived through the experience of sizing and developing the A380 aircraft to delivering and certifying components of that and in Airbus, and then went on to work in BAE Systems on a number of projects, including decarbonising regional aircraft with Embraer. I looked also in the past into hydrogen when I was working at Rolls-Royce in strategy and future programs, but quickly realised that it's difficult for a company that's been wedded to the kerosene option to jump. So I jumped myself and I joined GKN Aerospace, where I created a team of about 600, now currently working on something called H2 gear, which I call the first generation hydrogen solution with a power train that's basically working off liquid hydrogen. Mm-hmm. And now Fluxart's been created as a spin out that I developed whilst doing my MBA at Bath University, and working with a team out of Strathclyde and ex-Airbus colleagues who are building the future of a second generation hydrogen aviation solution, which is true zero emissions.
And when you say second generation, that's for aircrafts that will hit the stand or hit the runway in sort of 10 years time. Or what's the sort of if people aren't familiar with sort of aviation's technology development cycles?
I'm as ambitious as our disruptors and Universal Hydrogen and ZeroAvia, who saved, I think, me a little bit of pain because they've gone through the gaseous route and they've shown an aircraft can fly within 2-3 years of their conception. Now, I know that they are demonstrators, and certification, regulation, all that comes into it, and that will take a little bit longer. But let's just assume that their timeline and regulators can keep up with the pace, and they're suggesting 2028 for a 100-seat aircraft. Yeah. We believe by 2030, the reality will be that liquid hydrogen is the solution, and with liquid hydrogen comes a few more opportunities, actually, rather than the challenges that people might see with hydrogen. And that because, of course, we're carrying liquid hydrogen much more dense relative to gaseous, so you can get more on board for the volume. And also, you've got a cooling power, and that effect of cooling gives superconducting a real benefit. And we have a lightweight motor that's a quarter of the weight of traditional motors. And the propulsion chain also can be reduced massively in weight. We think the direct operating costs of our solution on something like an ATR 72 could be about 20-something% less. We believe that you could scale it beyond the 100 seats, which is where really the majority of CO2 emissions are being created. And it's been confirmed by IATA and others in recent reports, and ICCT, the International Clean Council of Transportation, that really we need to tackle the narrow body aircraft. And that's where we think that we can play into, because our motor doesn't just stop at 1 megawatt, it goes up to 2.5 megawatts. We might need a couple of additional motors on an aircraft to make it achieve a kind of a size of where maybe the sweet spot is, something like 150 seats. But that's where we're heading, and that's where we want to get to. And 2030 does sound challenging, but then there are quite a lot of players in this space now accelerating the pathways, and I think that's where we think we can get to with the first aircraft of our generation. Yeah, and we need it.
Yeah, certainly. I mean, in terms of that, the difference, I guess, between gaseous and liquid, and just not quite 100% clear on the advantage. Can you maybe just unpick the actual the advantage of liquid and how that gives you that? What was the term you used? ATR
72. So that's the regional aircraft that probably represents the largest part of the regional fleet. I would argue that also Embraer covers the other part of that fleet with their smaller aircraft. But I guess the question you ask, gaseous comes with the penalty of having to compress it, and you put large composite tanks to contain the pressure, whether it's 350 bar or 700 bar. These are large, weighty pieces of composite. And we think that liquid hydrogen in a basically double-skinned aluminium container can provide us with a much more power-dense solution, and the gravimetric efficiency could scale probably beyond 20-30% easily in the next 5 to 7 years. And therefore, we're really looking to bring range and then also the power effect that can come from the cooling. And what we talk about there is, you basically have minus 253 degrees, you take out the pressure, you're at 2 bar max, maybe you've got some boil off, so you contain the tank up to 7 bar. Basically, you've got this ability to turn that cold power that's sitting inside the liquid cryogenic temperature hydrogen into the cooling effect of the motor. What happens at, we call it high temperature superconducting materials and tape. We actually get virtually no resistance. So when that happens at that temperature, we get a conversion of power, which is, much, much more dense in terms of what you get power out for the current weight that you carry. So our motors can be a quarter of the weight of an existing motor that's electric.
Yeah, a quarter of the weight is a sizable advantage. And did you mention in terms of zero emissions, in terms of the emission profile from the engine has other advantages around the NOx or?
Well, so as I said, true zero, and our definition sort of aligns with what we're hearing from some consultants, whether they be the McKinseys or the Roland Bergers, they all seem to be descending on this phrase, true zero. And to unpick that for those that aren't aware is that if we burn anything, we create NOx. We also create sulfides depending on the source of fuel. E-kerosenes still also, whether they be from synthetic or bio stock, become, a need to remove that NOx or that contrails that go with it. In our solution, we don't have either of those. So we can bring a true zero, that means zero CO2 and the non CO2 effects we just talked about, to the table. And I think it's an option that we have to consider quite carefully, because if we're right, and the scientists in Reading and Manchester Metropolitan, like David Lees, are starting to highlight that potentially these non-CO2 effects are at least 4, maybe up to 8 times more potent to the greenhouse gas effect than we first realized, and certainly relative to CO2 itself. So with that, we start thinking hard about, keeping this option on the table, but we need to accelerate it. And that's what we're really trying to do, and looking forward to meeting people at the show and the conference over the course of the next few months, just to try and get ourselves a bit more acceleration in this pathway and get the awareness out there.
Yeah, certainly. It sounds fascinating tech. In terms of the creation of liquid hydrogen, do you think that could actually be more of a challenge than actually the usage of it?
Now, I'm working with Baker Hughes, who are one of the biggest liquefiers in the world for liquid natural gas. The strange thing is, if you want it at volume, it's easier to do than it is at sub-volumes. And at the moment, everyone's doing R&D in aerospace, but there's large volume off-takers that are beginning to appear. And I think our view is that this is the way to go. So you have to get the volume pulled through, and aviation in itself could take green hydrogen liquefied tons a day. Just in the UK, we've got about a 5-ton requirement right now, and that's just based on aviation. But when we start looking beyond R&D and towards the end of the decade, 20 tons a day at a regional aircraft location, which would be a regional hub airport, could easily be achieved. The compression technology already exists. The power generation needs to come from an electron, which hopefully is green, but it's possible. And in fact, the thinking is that distributed hydrogen production and liquefaction are probably the right answer. Speaking to a number of energy companies in North America, the likes of Chevron, just to name but one, BP, they're beginning to think about this really hard. Equinor in Europe. They're really thinking about how they can actually be part of the liquefaction process for hydrogen, because they've all got a journey towards hydrogen. and recognizing that the next step is to liquefy it to get it to aviation. I think that's an open opportunity.
Yeah, certainly. And I agree from everything that we've seen, that the decentralized approach would appear to be the best route, given likely only, I guess, aviation to require sort of a liquefaction of hydrogen. In terms of other impacts upon the form factor of your engine, have you had a look at that? Is I see behind, it's quite behind you on the logo, it's quite a traditional form factor, but are we going to see much more of a rocket shape, or the need to take in more air, or what are some of your thoughts around
I think the answers are really more about how we refuel these aircraft on the ground, because I think the challenge has always been for hydrogen, and we can see it in space. Refueling them is going to be one of those safety hazards that we know that we can get around, and that requires us to probably think about a form factor that goes back to the Comet, where you have maybe 2 entry points into the aircraft that keeps it separate from where you're refueling. I think there's going to be a different way in which the aircraft are going to be configured, with the tanks largely in the fuselage. There are some ideas around putting tanks back into the wing, but I think we're going to see longer, slender, maybe foldable wings. Within those wings, we think there's a large heat exchanger that's required that actually sits within the structure, and using things like additive manufacturing to create large amounts of surface area could possibly create new structures that both have form, fit, and a function to do with cooling. We also have another idea that you still want a tube and wing, but you sort of look at how you place the power units on the wing. We're more likely to have a couple more than you would have on a single aisle, but largely because we can scale to 2.5 megawatts right now. And that's, if you took an A220, you're probably talking about 15 megawatts. So basically you need, 6 of these. It's a different sort of configuration with that. And it's also a prop. And we think we still can get max sort of 7.78. So we're still getting decent speed in the air. That will be the one thing that we won't compromise on. Of course, safety will be the main one we won't compromise on. But other than that, I think actually most of the tech is with us. I think the wing and the structure of the heat exchangers and heat and thermal management is key. And that's what we're also working on with our partners.
Excellent. And in terms of sort of scaling up, is there a pathway to scale them up beyond that megawatt limit that you're currently working on?
So 2.5 megawatts is where we're heading to. We get there with our first variant step on the way, 2 megawatts, and then 2.5 by the end of the decade in a certified form on an aircraft. We're working with a couple of airframers that are significant, who are trading with us, because it's an interesting interaction. You can't just think of the propulsion unit in isolation. As I've kind of explained, you need the whole trade across the airframe and all the systems. Can you do something clever with the heat rejection from the fuel cells to warm the cabins, and do de-icing that's much more efficient? So you really have to do a lot more systems integration, and that's requiring us to work deeply in all the spaces that me and my team have been working on in the past, with our experience in Airbus and other companies like Rolls-Royce and GK.
Excellent. Fascinating stuff. It sounds amazing. And I think, clearly we're going to, I guess, enter a period of Cambrian explosion, if that's the right word, around the aviation form factors. And so, it's going to be fascinating to see. We wish you all success. And certainly, I think, certainly from the people that we've spoken to, the future seems to be liquid hydrogen. And we look forward to seeing you commercialize successfully and get your plane and off the ground. So, as I said, you're going to be speaking at the Sustainable Aviation Futures Congress, SAF Congress, which is 7th to 9th in June. We look forward to meeting you there and hearing more in depth about your work.
Thanks, Nadeem. We look forward to being in Amsterdam with you and the team.
Cheers. Take care, Paul.
Thank you.
Thanks. Bye-bye.